Hey, welcome. When you hear the word chemistry, you might be thinking of scientists in lab coats with bubbling beakers. But what if I told you the most amazing chemistry is happening right now, all around you? From the way your body digests food to the way your phone screen lights up, it's all governed by a kind of secret code. And today, we're going to start cracking that code together.
I mean, just think about it for a second. Milk turns into yogurt. A shiny new bike eventually gets covered in rust. You breathe in, you breathe out. We see these kinds of changes every single day, right? But have you ever really stopped to wonder what's going on behind the scenes? What's the invisible force that's making all this happen? Well, that's the big mystery we're diving into.
All right, so to really get a handle on these transformations, the first thing we got to do is learn how to sort them. Pretty much every change you can possibly see falls into one of two big categories. It's either a physical change or it's a chemical one. And this slide makes it super clear. Let's imagine you've got a piece of paper. If you tear it into a bunch of little pieces, what do you have? Still paper, right? It just changed its shape and size. That's a physical change. But what if you burn that paper? Poof, it's gone. You're left with ash and smoke. You can't get that paper back. That, my friends, is a chemical change because you've created brand new stuff. The very molecules themselves have been rearranged. And that whole process of a permanent, you can't go back kind of change, well, it has a name. It's called a chemical reaction. This is the engine that drives everything we've been talking about. It's like cooking. You start with your ingredients, we call those reactants, and you end up with a final dish, the products, which are totally different from what you started with. So, how can you be a chemical reaction detective out in the real world? Well, you look for clues. You ask yourself, did something change its state, like a liquid turning into a solid? Did the color suddenly change? Do you see bubbles of gas fizzing out of nowhere? Or did it all of a sudden get really hot or really cold? If you see any of those things, there's a really good chance a chemical reaction is underway. Okay, so we're getting pretty good at spotting these reactions, but how do we actually, talk about them? How do scientists from all over the world write down exactly what's happening so everyone's on the same page? Well, they use a special language. And that language is the chemical equation. The best way to think about it is like a recipe card. It's a universal shorthand, a cheat sheet that tells you exactly what ingredients you need, your reactants, and exactly what you're going to make, your products. It's the secret code finally written down for us to read. So, for example, you could write out a whole sentence. Magnesium reacts with oxygen to form magnesium oxide. Okay, fine. But the chemical equation, man, it is so much more powerful. Look at it. It tells us not just what, but how many. We need 2 atoms of magnesium, which is a solid, and 1 molecule of oxygen, which is a gas, to get 2 molecules of magnesium oxide, which is a solid. All of that info is packed into one tiny line. Now here's the thing. This language has one golden rule, one non-negotiable absolute law of the universe that you cannot break. Every single chemical equation has to obey it. And this is it, the law of conservation of mass. Sounds super fancy, right? All it really means is that you can't just create atoms out of thin air, and you can't make them disappear into nothing. The atoms can shuffle around and form new partnerships, for sure, but the total number of each type of atom has to be exactly the same at the end as it was at the start. So, let's take a look at this equation for iron rusting. Right now, it's a lawbreaker. It's totally unbalanced. Think of this as a little puzzle that we need to solve. We have to make sure that the number of iron atoms, hydrogen atoms, and oxygen atoms on the left side perfectly matches the number on the right side. And this table shows the problem plain as day. Look at this. On the left side, the reactants, we've got 1 iron atom. But on the right, the products, we have 3. And look at oxygen. 1 on the left, 4 on the right. Whoa, only hydrogen is balanced. This just can't be right. We've got to fix it. So, how do we solve this puzzle? Easy, we just go step by step. First, let's fix that oxygen problem. We need 4 on the left, so let's put a big 4 in front of the H2O. Great, but hang on, that just messed up our hydrogens. Now we have 8 on the left. No sweat, we'll just put a 4 in front of the H2 on the right side. Now they match. And last, we need 3 irons on the left, so let's put a 3 in front of the Fe. Now, let's do a final check. Everything matches. Puzzle solved.
And there it is, our final, correct, legally obeying, beautifully balanced equation. It now tells the true story of how 3 atoms of solid iron react with 4 molecules of water vapor to create 1 molecule of iron oxide and 4 molecules of hydrogen gas. It's perfect. All right, now that we know the language and its most important rule, we can start to learn the different genres of these chemical stories. Turns out, most reactions fall into just a few main categories. First up, we've got the combination reaction. And honestly, it's pretty much exactly what it sounds like. It's the getting together reaction. 2 or more things come together to form one single, more complex thing. A plus B gives you AB. Simple as that. A really cool example of this is when you add water to something called quicklime. It starts to hiss, and if you were actually there to touch the beaker, it would get really warm. That's because this combination doesn't just make a new product, slaked lime, it also releases a bunch of energy as heat. We call that an exothermic reaction. Next, we have the complete opposite, the decomposition reaction. You can probably guess this one. It's the breakup reaction. Here, one single complex thing breaks apart into 2 or more simpler things. AB splits into A and B. Take a look at this. You start with these pretty green crystals of ferrous sulfate. You heat them up, and this incredible change happens. The green color fades away and turns brown, and a gas is released that has this very specific smell, kind of like burning sulfur. That one green compound just decomposed into 3 totally different substances. Okay, now let's get into some drama. This is a displacement reaction. The easiest way to think about it is that a more reactive, or you could say stronger element, comes along and literally kicks a less reactive element out of its compound. It's basically saying, get out of the way, I'm taking your spot. This is such a classic experiment. You take a regular iron nail, and you dip it into this beautiful, bright blue solution of copper sulfate. And then you just watch. Because iron is more reactive than copper, it pushes the copper out. The blue color of the solution starts to fade away as it becomes iron sulfate, and the nail gets this brownish coating of pure copper. A total swap has happened right before your eyes. So what happens if everybody decides to swap at the same time? Well, then you've got a double displacement reaction. Here, 2 compounds meet up and they pretty much just trade partners. It's like square dancing for molecules, forming 2 completely new compounds. You have got to see this. You take 2 solutions that are both perfectly clear, like water, you mix them together, and instantly a solid white cloud appears out of nowhere. This solid is called a precipitate. In this case, it's barium sulfate. It's what formed when the new partners found each other. It is such a cool, clear sign that a double displacement reaction just happened. Okay, let's take a breath. We've learned the language, we've learned the big rule, and we've learned the main types of stories. So now, let's bring it all back to where we started, the world that's right outside your door. Let's see this stuff in action. All right, one of the most important kinds of reactions out there is called a redox reaction. It sounds a little intimidating, but the core idea is simple. It's all about a transfer. One substance loses tiny particles called electrons, we call that oxidation, while another substance gains them, that's reduction. And they always happen together. You can't have one without the other. This process is absolutely fundamental. It's how batteries power your phone and how your body gets energy from your food. And you see the effects of that oxidation half of the deal literally everywhere. That rust on iron we keep talking about, that's corrosion, and it's caused by oxidation. Ever open a bag of chips and they have that awful stale taste? That's rancidity, from the fats and oils oxidizing. Even when you cut an apple and it starts to turn brown after a few minutes, yep, you guessed it, that's oxidation too. So, I want to leave you with this final thought. The next time you walk past a rusty fence or you see a slice of apple turn brown, what are you going to see? Are you just going to see rust, or are you going to see the invisible dance of atoms, a balanced chemical equation playing out, a real-life redox reaction happening right in front of you? You now have the keys to the secret code. You can see the world not just for what it is, but for the incredible chemical stories it's telling, all day, every day.